So, welcome to another interview with somebody who has just finished the Zero to ASIC course, and this time I'm talking to Uri. So, how are you doing today, Uri?
Hey Matt, I'm doing fine. Finally, a bit relieved after taping out all the projects for MPW4. So now I have some time to talk about them.
Yeah, and you did do quite a big, extravagant submission for MPW4, which we'll get on to later on in the interview. So, for now, could you tell us kind of what you do on your day to day when you're not doing ASIC stuff?
So when I'm not doing ASIC stuff, I'm doing mostly electronics, but virtual electronics. I work on an online simulator for Arduino and electronics called Wakui, where you can just grab a virtual Arduino or Raspberry Pi Pico ESP32 board, connect a bunch of parts, wire them, write some code, press play, and see the result. So pretty much digging all day into electronics and all kind of sensors and protocols and whatever.
Yeah, and we met through the Hackaday Remoticon, and we both did talks for that. And I'd recommend people checking out your talk where you were talking about reverse engineering the ESP32 Wi-Fi stack to add that into the online simulator, which is awesome. And I'll put a link in the description if you want to check that out. But I would recommend it. It's a great way to play with microcontrollers and hardware without actually having stuff on your desk. And one of the super cool things was being able to plug in a virtual logic analyzer, capture signals, and then download the VCD file and being able to look at the traces. I thought that was a really great touch.
Thanks.
Yeah, so that's where you heard about the course. Could you say a bit what why you wanted to do the course, what you wanted to learn?
So doing my own ASIC was some idea that sneaked into my mind like 4 or 5 years ago, and I started researching it. And usually you can't do it without a lot of capital and patience. I think custom ASICs start at thousands of dollars, and then you have to wait a couple of months. Not something that somebody would do as a hobby. And there is also a lot of specific expertise that you need in order for that to be maybe successful. Because if you have no idea what you're doing, there is no way you will spend that amount of money and wait a few months just to get a brick. Um, so when I heard about the opportunity to get my hands dirty and uh, do something, try it, and it would basically, thanks to Google, cost nothing. And then there was also your course ASIC to Zero, which I hope we'll find out when the chips arrive, but give me enough expertise to do the design and get something that has a chance of working. It was like, okay, this is a perfect fit for what I wanted to do for some time already. Um, so this is when I decided, yeah, let's give it a try. Worst case, I will have a couple of bricks and a lot of new experience.
Yeah, yeah. So you actually went through the course really, really quickly. I think you joined maybe a couple of weeks before Christmas, and then we had the tape out at the end of December, and you've got 3 designs in there. So, did the course satisfy your desires to learn?
Yeah, I think the two highlights of the course for me was first that it was self-paced, so I could just I had a week where I had some free time, so I could just go through the chapters and do things as fast as I wanted. Basically, go back and forth and just sort of customize the course or learn it in the way that I found works best for me. And then the second thing was your availability and the other members of the Discord community who just, whenever I got stuck, and uh, you can't help it. There is like so much new tooling and new terms, you will eventually get stuck and need some help. So whenever I got stuck, I just posted a message, and usually within minutes, I would get a response that would keep me going. So I think these two things were the most valuable parts of the course for me.
Yeah, it was actually really cool the interaction that we had on the Discord server. It felt like I could really kind of feel your progress going through the course, depending on the questions you were asking. It was great. So, would you recommend the course to somebody else?
Yes, and I would say the course is giving a good starting point, but you still have to you still have to be passionate about it, and you still have to be driven and motivated, because this is not simple. This is a lot of material, and you did a really great job compressing it, but still the students need to sort of decompress it in their expand it in their minds, and try like I think if you learn Verilog in the university, that takes probably a whole semester, and here it's just like one topic in a 5-week course, or I don't know how you frame it, but um, there is a lot of to learn, and you have to be prepared to spend the time. And um, eventually, I think I personally got the most benefit from just trying to go through the process myself, and submitting a project, and then another one, and then even one more. And this is where you hit the all the obstacles that, you know, in theory things work one way, but then when you get to real life, engineering is all about trade-offs and overcoming limitations with workarounds. So that's where you sort of hit all those non-trivial things that even the best course wouldn't be able to touch everything.
Good insight. I agree with you about engineering being a compromise as well. Maybe that's one of the differences between maths and science and engineering. Yeah, so let's move on to your practical experience of getting to tape out. So yeah, congratulations on getting 3 designs in. That's a first for the course. So you did a custom CPU, a Conway's Game of Life executed in Silicon, SILIFE, and you did a skull-shaped MOSFET, a new standard cell that you then made NAND and inverters out of. So let's start off with the custom CPU. What can you tell us about that?
Okay, so the custom CPU was my first project, and I wanted to go with something that is, on one hand, not too trivial, but it wasn't too aspiring either. Because what you usually would make with ASICs is custom CPUs. That's very common use case. And I went with a very simple CPU that would run an 8-bit CPU, and it ran machine code that I created for this spooky guy. This is a hardware CTF riddle I created a year ago. And some part of the riddle is a cryptic function called spell that looks, the source code looks like a skull, and it runs an 8-bit virtual machine that is executed on this 80 tiny chip here in the middle of the skull. And I try to implement this virtual machine language called spell in ASIC. Um, it was pretty straightforward. I think I had a basic implementation in Verilog in a day or so, but then learning how to connect it to the Caravel harness, to the management sock, that is a RISC-V thing, through a bus called Wishbone, and learning how to make those things work together and writing all the test cases and making sure that I implement all the things right using formal verification. It was a great way for me to apply what I learned through the course with a project that had sort of limited scope, but was, on the other hand, pretty comprehensive.
Yeah, and they kind of came out around like the average size that we see for group submissions on the course, so around about 300 or 400 microns square. And from my memory, you didn't have too many problems with getting that to get hardened or meet timing and stuff like that.
Yeah, there was like a few adjustments that I had to do, and that's where your input was very valuable because there is no way I would have figured this out so quickly without a very good knowledge of how the hardening process works and the tooling. But once we got that figured out, it wasn't too complex, and it also hardens in like 5 minutes or so. So the iterations are pretty fast.
Yeah, yeah. Yeah, so just to get this straight, so on the AT Tiny, you have like a virtual machine written in C that then can run your special firmware. But now what you've done, instead of having to have a virtual machine, you've actually made the real spell hardware.
Right. So you can
Super cool
write your
project.
own spell code and run it on a chip if it works out.
Native spell. Nice.
Native
Yeah, I like it a
spell.
lot. Okay, so then project number two was a lot more involved, Sea Life. Can you tell us about that?
Yeah, so one of the cool things about ASIC is that unlike CPUs, where they can run opcodes and they do it sequentially, ASICs can run things in a very high level of parallelism. If you have like a simple unit and you just replicate it 1,000 times, then you will get the same thing running 1,000 times. And I was looking for some problem that is easy to break down into smaller units, and those smaller units are sort of independent. And I don't know. I think it's also I was also inspired by something I saw in Remoticon. One of the speakers, Voya, I think is his name, has his built a very a big game of likes LED metrics, and he hangs it on
That he has in the
his
background,
wall.
doesn't he? Yeah. Yeah.
Yeah, so I was like, Game of Life, that seems like a good fit because you have all those single cells, and the state of every cell depends only on the states of its neighbor. So it's something that you can basically break out into smaller cell units and then connect as many as you want together. And I was like, yeah, once I have a basic cell unit and I have like the recipe for connecting them, I could just scale it to fill all the space I have in the silicon. And initially, I started with 8 by 8 grid, and that worked really well. It hardened in like 3 or 4 minutes, and it consumed like I think even less, 160 by 160 microns or something like that. And it was like, okay, so I can just fill the entire silicon with that, and I'm done. But then I realized the tooling would really choke. As soon as I got to 32 by 32, it would run out of memory. And then I had all sort of, I hit all sort of like walls trying or ceilings trying to get the larger versions hardened, crashed my machine a few times.
I
And
remember your epic run of 85 hours, I think.
yeah, trying to get the routing done. It ran for 85 hours and never finished, like it failed. So eventually, the idea of let's take something simple and replicate that a lot of times wasn't really working. I had a very small version working and it worked well. I wrote some cool harness in GDK Wave where you could actually see the metrics just by ASCII character space and asterisk, and it worked well. But then when I tried to scale it, it would just explode. And eventually, I figured out that if I didn't do the scaling of the grid in Verilog using parameterized functions, but rather created a custom Python code that would generate the Verilog, that helped the tooling with the memory issues somehow. And I managed to get a 32 by 32 grid hardened that takes roughly 30 minutes. So the iterations were still slow, like 30 minutes for every change. But then I realized that I could probably take a few 32 by 32 blocks, grids, and somehow connect them. So I couldn't go higher because as soon as I tried to go bigger, the tooling would just never finish running or explode because out of memory or whatever. But I just tried to take this block of 32 by 32 and replicating it. And that also didn't work out because using custom macros, which means you have the design ready for a part and you just use it multiple times, that's also a pretty challenging task. So I decided to do something different. Instead of having the same design replicated within the same chip, I decided to try and create an interface where you could just take several chips and connect them together. And then after each generation of the game of life, they would communicate across the array of 32 by 32 grids and synchronize their states. And well, that was another challenge.
Yeah, you definitely went for it on this one.
Yeah, so it's a bit too complex to just explain in a few minutes. So I'm now writing a blog post explaining about all the technicalities of like synchronizing the different chips that run those 32 by 32 grids, and also how I made an interface that would allow you to serially load the initial state throughout all the different chips. So stay tuned.
Yeah, looking forward to that blog post.
And I think we finished hardening Sea Life like just a day or two before the actual tape out date. So it was really tight to get it ready, this 32 by 32 with all the synchronization in time. But we did it. We just need to wait 6 months to see if it works.
And that wasn't even your last one, actually. And now I'm thinking about it, you actually did two more. So now tell us about Skullfet.
So you have already seen that I have some obsession with skulls.
Skulls. Yeah.
And the first module in the course talks about the basics of drawing the cells, those not game of life cells, but logic cells. Those are like the building blocks that you use to build your silicon chip, or at least digital designs on your silicon chips. And there was an exercise where you had to draw a MOSFET transistor just by drawing the different layers. So then it came into mind that I could probably do something cool with it. Maybe make a MOSFET with a spatial shape, like the shape of a skull. And it turns out this is possible. I don't know how well it would work. Like there are a few things that might not be very good in like physics, like the holes for the eyes of the skull in the silicon layers. We'll see. I think I first submitted, created an inverter and then a NAND gate out of 4 different skulls. And then we added it to the group project. And that was done like a day before the final deadline for the tape out. So I had one more day, and I was like, can I get this even bigger? Like the skull head is very small. I think 10 microns by by 5 by 2 microns or something like that, super small. So even if we had decapped the chip and looked inside, we couldn't really see it without scanning electron microscope or something like that. And I was like, what would happen if I would scale it? So as a last minute submission, I tried submitting my own project to Caravelle. Just one made a very big area with a small skull in the corner. Again, two inverter and one NAND gate, all skull shaped. And then I also tried to take the design of the skull fit and just scale it by 10x, so make a larger skull inverter. But it turns out this wasn't as trivial as just scaling the whole thing, because there are like DRC rules that mandate specific spacing or specific distance between elements, and then I had like to adjust the design to make it possible for to make the DRC happy, to make it possible to be manufactured and hopefully working. And I also wanted to do a supersize 100x skull, but that didn't work out with the DRC, and I ran out of time, so I just made it on the metal layer. So it's a non-functional skull fet, but it's still there, so you can probably see it with a microscope, with an optical microscope. I don't know. We'll see, or not.
Yeah, I think for MPW1, eFabless was shipping bare dies as well as the wafer level chip scale packages, and I think you would definitely be able to see it with just your naked eye if they continue sending dies. Yeah, so not the fastest or most performant inverters, but definitely the scariest ones. So yeah, congratulations for getting all of that stuff in and also making your own application, which I think is a good sign of that you've not only learned some new skills, but you can actually, on your own now, you've got everything you need to.
You could say I just wanted to make my own barebone transistors.
A nice pun. Great. Okay, so I think that's about it. Is there anything else you want to add before we close this interview?
Well, I think other than being a great opportunity to get your hands dirty with your own silicon design, which wasn't really a possibility for makers up to now, it's also pretty amazing to see the sort of ecosystem starting to emerge. People build a lot of utilities, and for instance, in my Spell processor, my first project, I used OpenRAM, which is an open source implementation of SRAM, and there was also one of the I think it was Pavel from the community who created like a small shim that would allow the project to speak to the SRAM while to the OpenRAM, while the CPU could also speak to it. So it's more than an opportunity to learn how to do this stuff. It's also about the ecosystem that is coming to life.
Definitely exciting times to be alive in the world of open source silicon. Great. Well, thanks very much for your time, Uri. And yeah, I'll see you around, I'm sure, on the Discord, and look forward to your future submissions.
MPW5.
MPW5.